Hello, thank you for the opportunity to present. I'm sorry I'm not there. I'm located in Siilijärvi right now. So I'm Teemu Karlsson. I work at the Water and Mining Environmental Solutions unit at GTK in the Kuopio office. And yeah, I've been working on this subject since 2011, more or less same group. So, well, this 20-25-ish minutes is a bit short time to very thoroughly go through all the topic, but I'll shortly present the extractive waste types, especially waste rock and tailings, as they are the main ones. A little bit about their properties and potential environmental impacts, concentrating especially on the forming of acid mine drainage. Then I'll tell a little bit how to characterize different waste types and basically how to predict the formation of AMD. In the end, a little bit about extractive waste legislation, especially about the definition of inert extractive waste, and then a bit about mine waste management, like prevention and reduction of the amount of extractive waste. Extractive waste, it's one of the main waste flows in the world, and in Finland there's around 100 million tons of extractive waste generated every year. This is 3/4 of the total amount of all waste in Finland. And well, this waste mountain needs to be managed, and the management is one of the main challenges for the mining industry. Most of the extractive wastes is waste rocks, tailings, some other possible mine waste types which are not so thoroughly presented here are, for example, the overburden, like tills that are on top of the deposit, water treatment or process precipitates, or slags or ashes, for example. And well, the main challenge is related to the fact that the amount of extractive waste is so huge. It can be quite reactive, and the environmental impacts caused by the waste, they can last for a very long period. Waste rock is generally bedrock that has been mined and transported to get access to the valuable ore. So the waste rock usually doesn't have any economic value. It's coarse grained material. The boulders can be like in meter diameter. And in Finland since 16th century, around 1,300 million tons of waste rock has been generated. Most of it during the past 50 years and over half during the last decade. So the amount of generated waste rock is getting higher. Usually it's deposited in heterogeneous piles, although separating different rock types to separate piles has become more common, which is good. Tailings, on the other hand, it's very fine-grained material. It's material left over from the ore processing process. So when the ore has been crushed and ground, most of the valuables are taken away in the process. The leftover is tailings. There's over 500 million tons of tailings in Finland, generated since the flotation process was introduced in 1911. And tailings are commonly deposited in tailings ponds, although this dry stacking is an emerging method also. So there you can deposit in more like in piles. This Tukes, which is the authority that supervises this kind of mining operations, they every year publish statistics about the amount of extracted ore and waste rocks. And for example, in 2023, in total, 46.8 million tons of ore was extracted and 81.3 million tons of waste rock in Finland. This doesn't include smaller natural stone quarries, for example. And part of the statistics table is there. And as you can see, most of the produced ore and waste rock comes from metal mining. I'm sorry, it's in Finnish, the table, but these are the 8 metal mines that were in operation in 23. But there's few other large mines also that produce ore and waste rock. For example, Siilijärvi apatite mine is probably one of the most significant outside of this list of 8. There's also quite large dark nickel mines, carbonate mines that also produce extractive waste. So the amount of waste rock can be seen from the table, sivukivi, on the rightmost column, but the amount of tailings is not there straight. But when considering that usually the valuable element concentrations in the ore, they are usually around 1 to 2%. So then the rest of the ore is basically tailings. As said, extractive waste, they can be a major source of environmental impacts. Here's a generalized conceptual model about the sources, pathways, and receiving environment, taken from this card guide that you might want to visit. The main sources are the extractive waste facilities, tailings ponds, and waste rock piles, basically. The main mean of transportation is water. So drainage, first the rain goes through the waste material and drains to environment, to groundwater or to surface water. Also dust can be an important emission, but here we concentrate more on water. Of the different extractive waste types, especially the ones that contain sulfidic minerals are problematic. And that's because the exposure of these sulfide minerals, which especially the iron sulfide, to oxidizing conditions, for example, the atmospheric oxygen and water, this might generate acid mine drainage, which is usually shortened to AMD. Also, acid rock drainage, ARD, is words that are commonly used. AMD is usually characterized by low pH and high harmful element concentrations. There are different kind of sulfides. They don't behave in similar way. From that list on the right, you can see that some sulfides generate more acid, some don't actually generate acid at all, at least in more or less neutral conditions. And also the oxidation resistance varies, pyrrhotite being the most reactive. It depends a little bit. For example, some trace elements in those sulfides might affect the reactivity. The quality of the water that drains out of the extractive waste largely depends on the mineralogical and chemical composition of the waste material, especially on the ratio of acid-producing and neutralizing minerals. Besides the ratio, other things that affect are the exposed surface area of the minerals, or are the minerals encapsulated in some minerals that resist oxidation or weathering better, for example, inside some silicates, and so micro textures and so on. All these kind of things affect. And the mobility of harmful elements, it's usually related to sulfate oxidation. Either they are originated from the sulfides, or then they are originated from other minerals that are leached by the acids generated by the sulfide oxidation. The main acid-producing minerals in Finland are pyrrhotite and pyrite. Pyrite produces a little bit more acid, but pyrrhotite is more reactive. The main neutralizing minerals are usually carbonates, like calcite. But especially in Finland, where many rocks don't have that many carbonates, also some slower reacting silicates might be important sources of neutralization, like micas and chloride, but especially calcium and magnesium bearing silicates. And then it should note it that even if there's enough neutralization and the pH of the drainage is neutral, there still might be elevated concentrations of harmful elements, and in this case the drainage is usually called neutral mine drainage, NMD, which is actually quite big problem also. Maybe more should be talked about that, NMD. So some extractive wastes are more harmful than others. So the management methods can also vary case by case. In general, extractive waste coming from a sulfide deposit has more risk compared to for example, oxide deposits or some industrial mineral deposits. And all different kind of extractive wastes need to be characterized. Data from characterization, so basically how harmful some waste type is. Is it very prone to produce acid, and will the harmful elements mobilize? that kind of data is needed already in a very early phase of a mining project to make the first environmental applications and to design the waste facilities, for example, what kind of basal structures there should be, what kind of water management is needed. And one important thing is also to evaluate if there's some possibilities for utilization of waste materials. And also closure plans need to be presented quite early. Those include, for example, cover structures. The bad thing is that the prediction of AMD can be hard because the final drainage quality depends on so many things, like mineralogical, chemical, hydrological, microbiological, biological factors, that it's quite hard to predict the drainage quality very thoroughly. But however, some characterization has to be made. There's different levels. Basically, you start with geochemical laboratory tests or static tests. Then after those, you go to longer term kinetic tests. Then maybe do some geochemical modeling to upscale the results. And then one way is to utilize analogies from similar already existing extractive waste sites. So here's a little bit about the first phase, I would maybe call screening phase of the characterization. You should know for the rock type, do some mineralogical analysis, like XRD, SEM studies. You should find out the sulfidic sulfur content. Then the potentially harmful element concentrations. Here are the so-called PIMA elements mentioned. And especially interesting is to find out to which minerals these harmful elements are bound to, so you can assess the risk for mobility. So with mine waste, this two-stage batch test, which is common for regular waste, to classify it and see the mobility of elements, it doesn't really work. You can have quite low quality fresh waste rock, and if you do that two-stage batch test, which is basically just a water leach, it might be that all the values are below detection limit. So this waste type is a bit special. Then you should assess the acid production potential and neutralization potential to see if the material is prone to produce acidic drainage. You could also check if there's other harmful substances like asbestos, which is quite common. Usually the first phase characterization is done for like a bigger amount of samples, like to screen a little bit the mine waste. And then for this second phase and forward, testing goes more or less amount of samples, and you know a little bit what are the most interesting waste fractions. The most used kinetic test in mining environmental studies is humidity cell testing. One reason is that it's the only standardized method. In the test, around 1 kilo of crushed sample will be put inside a cell. It will be watered regularly, and then drainage is sampled every week. Usually, or the minimum duration of this test is 20 weeks. 40 weeks is quite usual. The problem with this test is that sometimes it's a bit hard to say when you should stop the test. Some have been running this test for several years. But quite often after 20, 40 weeks, you can already say something about the mine waste. Usually other long-term and large-scale tests, they have to be designed case by case. For example, column tests or field scale lucimeter test or test piles. It's always a case by case study, basically. And duration of these field tests can be several years. Then when you have some results, you can do geochemical modeling to understand the processes that are affecting the drainage quality, and maybe to upscale the results to field scale. The Finnish government decree on waste from extractive industry, it gives a framework for extractive waste classification as inert. Basically, the decree says that the waste shouldn't dissolve or break up or change so that it can cause a danger or harm to environment or human health. Sulfidic sulfur concentration should be maximum 0.1% or 1% if the acid production neutralization potential ratio is higher than 3. It shouldn't self-ignite or burn. Well, this is usually not the problem in Finland. And then the concentrations of these potentially harmful BIMA decree elements should be below those threshold values mentioned in the BIMA decree. I will show them shortly. And the waste shouldn't contain any other harmful elements or chemicals used in processing that could cause danger or harm to environment or human health. Here are the threshold values for the BIMA decree elements, and it's a bit problematic. First, the study or the document that gives these values says clearly that this is meant for polluted soil, not for mine waste. But then again, here we are using them. We don't have any other threshold values, so we are stuck with these for now. And in general, it would be quite hard to create such a strict list of strict values, threshold values, because it's so case by case and depends where which minerals the elements are bound to. For example, in quite many mine waste samples, the chromium and vanadium concentrations are quite high, well above the threshold values, but they are usually bound to oxides that don't really weather in its nature, so they are not as problematic usually as some other ones. And then again, I've seen cases where the nickel values have been, or the concentration have been below the threshold value, and still it had caused some harmful drainage. Also, the legislation gives possibility to create a national list of inert extractive waste. So basically, that kind of rock type should usually, well, they should be as listed here in this classification table here. And the idea of creating such a list was to ease the utilization. Here's the list that was created over 10 years ago. So basically, if you have like granite, based on legislation, it should be okay to utilize without further studies. But you have to always make sure that it doesn't have lots of sulfides, even though it's on this list. Well, if you want to see this Finnish government decree on extractive waste more thoroughly, here's some links, but I'm not going through it in more detail. Then, for the end of the presentation, a few slides about how to prevent acid mine drainage. The main way of minimizing the oxidation and mobilization processes and the formation of AMD is basically to prevent the exposure of sulfide minerals to atmospheric oxygen and water. For example, by covering the waste with some layers or water also. Gradual closure of the waste facilities, it's also one, maybe an emerging method. Hasn't been too much practiced in the past, but the idea is that the waste area wouldn't stay without cover the whole time of when the mine is active, but you could start already covering some parts during the operations. So that would decrease the amount of time that the material is there. Also, at some cases, they have used alkaline materials to neutralize acidity, like they have mixed the lime to tailings, sand, and so on. This is maybe my favorite way of managing mine waste. So the amount of the extractive waste should be reduced, especially through utilization. I think there's lots of potential to utilize mine waste. Currently, quite low amounts are being utilized, mainly in earth constructions and cavity filling at the mine sites. There are some exceptions. For example, well, obviously the carbonate mines, Nordkalk, they have quite high percentage of utilization of their waste. And also, for example, Kemi and Laiva mines, they have recently nicely used their waste rocks outside the mine site also. One possibility would be to utilize some good quality extractive waste in cover structure as part of the cover structure, for example. This would decrease the need for natural materials like till, because if you have a 100-hectare waste facility and you want to cover it with 1 to 2 meter layer of till, that's a quite amount of till, and to get it, you might need to dig a pit somewhere and transport the till also. So that has also some environmental impacts. One way is to reduce the extractive waste is more intelligent processing and landfilling. And the separate extractive waste fractions should be deposited to certain places. And the idea is that you know where what kind of material is. So if you want to reuse it later or utilize it, then you know where to go. And of course, the best quality fractions could be utilized right away. We just started a Syntem project that's touching this topic. The main idea is move rocks only once. You should also check that one. And one raising issue is remining of old sites, because there's need for critical minerals. But so far, we haven't really found too many old mine sites that would have such mine waste that would be really economic to remine. Only the Otanmäki tailing site is an exception. There might be enough ilmenite to reprocess the tailings. You can see the Futuram page there, which is dealing with this topic. And then last slide. There's
Teemu,
one.
Do you have 2 minutes?
Okay. Well, yeah, I have 2 slides also. So traditional waste disposal methods, they usually mean that you deposit waste rocks in one place and tailings in one place. And this co-disposal of extractive waste is an emerging method. So basically you combine the waste materials to one area. It has some potential benefits and also challenges. Benefits could be, for example, that there's the area needed for waste facilities is smaller. The tailings can maybe the geotechnical stability might be better. Air won't flow inside the waste rock as easily, so that would prevent the generation of AMD. But it also has some challenges. For example, it's mixing the waste streams might be not so easy. Or if you want to reuse the mine waste, then that's not easy again. This hasn't been practiced in Finland yet, but there has been some plans. And just a few pictures of why tailings on geotechnical stability matters. So it might be a bit hard to construct cover structures, for example, if the tailings is not very stable. Thank you for your time.
Thank you.